Hi, and welcome to our crash course on trigonometry. This crash course is one of 3 in a series of videos talking about trigonometry and trigonometric ratios. The first video, we're going to be talking about trigonometric ratios in a right triangle. In the second video, we'll be looking at the law of sines and the law of cosines for any triangle. And in the third video, we're going to be looking at the area formulas for a triangle using the trig formula and Heron's formula. This video is really, or the series of videos is really for secondary 4 students, but anybody in secondary 5 or even post-secondary education could use this as a good refresher. To start, we're going to take a look at defining the trigonometric ratios in a right triangle. So you see here that I have gone ahead and drawn us a right triangle. And in order to use these relationships or these ratios, I first have to establish what my angle theta is. So in this case, it's going to be this angle right here. So we're going to look at how to use our ratios in relation to this angle theta. In the first bit, we have the sine ratio. So it says sine theta is the measure of the leg opposite angle theta over the measure of the hypotenuse. In a right triangle, the hypotenuse is always the longest measure, and it's the one across from the right angle. So that will be the same all the way through our trigonometric ratios. In this case, once we've established where theta is, you'll see that the leg opposite the angle theta is the one directly opposite it. So when we talk about the measure of the leg opposite angle theta over the hypotenuse, those are the 2 measures we're talking about. We abbreviate it to sine theta is equal to O over H, which is where we get the SO part of the acronym you see above, SOH-CAH-TOA. We go down to the cosine. Cosine theta is the measure of the leg adjacent to the angle theta over the measure of the hypotenuse. So back to theta, this is the line or the leg adjacent to theta. And of course, that's over the hypotenuse here. Cosine theta is abbreviated to A over H, which is the CAH part of our acronym. Finally, we have tan theta, which is the measure of the opposite leg over the adjacent leg, which gives us the tan theta O over A, which is the TOA part of our acronym. So there you have it. You have our 3 trigonometric ratios in a right triangle. Now, it's important if you're going to use these ratios that your calculator is in the degree mode. Otherwise, your values are not going to be correct. And the beauty of these ratios is that it doesn't really matter. The lengths of your legs don't matter because the relationship sine theta, cosine theta, and tan theta are constant for any given degree of theta. What I mean by that is, say my theta is 20 degrees. Well, my sine, my cosine, and tangent of 20 degrees is going to be the same whether or not I have these really short legs or long legs on my triangle, which makes it super useful when we're trying to use them to find a missing length in our triangle, which of course we're about to do. We're ready for our first example, which is actually the only example in this video. And we're going to be looking for the measure of the side AD, right? Now, looking at the measure of the side AD, we see that AD happens to be the hypotenuse of this larger right triangle ABD. We don't have enough information as it is to figure out what AD is, so we have to look at what else is there and kind of plan an attack. I notice that I have a smaller right triangle right here, AEF, and that's sitting within the larger one. So it shares the common angle A with the larger right triangle. And I also happen to have 2 known measures on that smaller right triangle. So I can use some of my trigonometric ratios to figure out what AF is, which would give me enough information. Okay, if I have AF, then I can find the entire measure then of AB. So with that shared angle and that entire measure AB, I would then have an angle and a leg on my bigger triangle, which would allow me to go and get that AD measure that I'm looking for. So now that I have a plan, I just need to put it into motion. Here we go. I'm going to start by finding the measure of angle A. So angle A is actually our theta in this case. And so I'm just going to identify it on my diagram so we all know really clearly where it is. It's this angle right here. And because I have the angle, the measure of the leg opposite to my angle and the measure of the leg adjacent to my angle, I'm going to be using the tan ratio for this problem. So tan A is going to be equal to the measure of EF, which is 3.36, over the measure of AE, which is another given, 4.98. And that is what I'm going to be using to calculate it. Now, the thing is, I need to isolate for the angle A. So in order to do that, I actually have to use what's called the arctan function. And on your calculator, it looks just like that. It's tan to the exponent -1. So I'm going to be looking for the arctan of 3.36 over 4.98. If you're having trouble finding arctan on your calculator, it's often the second function of the tan button. Any scientific calculator will have arctan, so just keep looking, okay? When I punch that into my calculator, it gives me a value of approximately 34 degrees. So it's not quite 34 degrees, it's actually got a few decimal numbers, but I'm going to round it for our purposes to 34 degrees. So here we go. This is what I'm going to carry forward in the rest of my calculations. So now I have that measure of my angle A. I can now use that to find the measure of side AF. So I'm just going to create a little space for myself here by erasing my previous work. And in order to find the measure of the side AF, well, AF is the hypotenuse of this smaller right triangle. And so I can find that measure by using the sine ratio. So that means that the sine A, which is actually the sine of 34 degrees, which is my angle A here, is equal to the measure of EF, which is the measure of the leg opposite to angle A, and that is 3.36 centimeters over the hypotenuse AF. And because AF is our unknown in this scenario, I want to actually manipulate the formula a little bit to give me AF isolated on the left side here, and on the right, I now have 3.36 over sine 34 degrees. Perfect. Simple maneuver on my calculator, and I get the measure of AF, which is approximately equal to 6.01 centimeters. So I'm going to write that in on my diagram here, 6.01 centimeters. Great. I now have everything that I need to know to find the measure of the side AB. So because I have AF and I was given FB, that's going to allow me to find the entire distance AB. Just erase my previous work. And that's what I'm going to go ahead and do. So the measure of AB is equal to AF, which we found to be 6.01 centimeters, plus the 3.15, which was given to us in the problem. When I add those two numbers together, I get approximately 9.16 centimeters. So that means that the whole distance A to B is 9.16 centimeters. And this is perfect because that is now giving me enough information on my bigger triangle ABD to find my missing measure AD. So I have the common angle, 34 degrees, and I have this leg here, 9.16. So I am going to go ahead and use that to find the measure of AD. This time, it'll be the cosine ratio that I'm going to use. So I plug in what I have. I have 34 degrees. So cosine 34 degrees is equal to the measure of AB, which is the 9.16 centimeters that we just calculated, over the measure AD, which is the length that I'm looking for and the hypotenuse on the larger triangle. I have to manipulate this equation to isolate for the measure AD, just like that. So I end up with 9.16 over the cosine of 34 degrees, and punch that into my calculator to get the final result of 11.05 centimeters. So that means that the measure of the side AD is 11.05 centimeters. So I'm just going to put that on my diagram right here. And I'm done. So that's it for this video on trigonometric ratios. Stay tuned for the next video in the series where we're going to be talking about the law of sines and the law of cosines that apply to any triangle.